For this tutorial, we're going to go through how to calculate a cardiac axis from a 12-lead ECG recording. This isn't a difficult thing to do, but when you're starting out, it can be quite confusing. There are a lot of different steps involved, a lot of concepts behind it, and if you want to get the correct result, which is very important, you have to know how all of these things work together. And by the end of this video, you should know exactly what you have to do to calculate a cardiac axis, and you'll be able to go off and practice on your own, and before you know it, you won't even need the hexaxial reference system diagram because it will be stored in your head. Okay, so let's calculate the cardiac axis. Okay, so with the human heart, we have 4 chambers. Alright, so we've got the left and right atrium, the right ventricle, and the left ventricle. Okay, now in order for the heart to contract, these cells up here in the sinoatrial node, they spontaneously depolarize, okay? And the signal that they generate is transmitted across both atrium and also to this junction here. Okay, now this is the atrioventricular node, AVN. Alright, now once it's reached there, it travels down the ventricular septum to the His bundle. Okay, and then it bifurcates. So down the left bundle branch, the signal is carried up to the Purkinje fibers here, depolarizing in that direction. And down the right bundle branch, we travel up to the Purkinje fibers in the right ventricle. Okay, so as we're doing now, when we look at the heart from the front, that wave of depolarization effectively starts at an 11 o'clock position and travels down this way to 5 o'clock. So any problem that affects this system at all can be assessed using a 12-lead ECG and what we call the hexaxial reference system, because obviously any problem that there is in this pathway will inhibit this 11 to 5 depolarization movement. Now, we already know the leads that make up our hexaxial reference system. Okay, we've got the standard limb leads, the augmented limb leads, and that's it. Alright, so don't worry about the chest leads for this instance. When you combine the vectors that they comprise of, you get this circular diagram. Alright, now we quantify the cardiac axis in degrees. Okay, and each of these lines on this diagram is assigned a value. Okay, and they also represent a lead from one of the 2 sets that we've discussed. So over here we have lead 1, which is a starting point of 0 degrees. You come down here, we get lead 2, which is 60 degrees to the positive. So this obviously positive 30 degrees. Down here we have AVF, and a value of plus 90. One further along, lead 3, which is given 120 degrees. And if we come all the way up here, we have AVR, which is a value of 150 degrees. Below here, opposite lead 1, or rather at the end of the negative end of lead 1, we have plus or minus 180 degrees. Okay, simply because it's opposite the positive end. And over here we have AVL, and that gets a minus 30 degree value. Okay, this diagram is split into 4 separate sections, okay, and each one represents an area of axis deviation. So from minus 30 to plus 90 at AVF is what we consider normal. -30. To -90 represents left axis deviation, or LAD. From ±180 back around to AVF at +90, we have our right axis deviation area, and finally the remainder from -90 through AVR to ±180 is our extreme axis deviation, or far axis deviation. Now, in order to calculate the conduction axis on an ECG trace, we're going to want to assess the leads that you see on the hexaxial reference system diagram, okay? So, leads 1, 2 and 3, AVL, AVR and AVF. Alright, so if we get a 12 lead ECG recording like this one, we'll be looking at this lead, and this lead, then your augmented limb leads, AVR, AVL, and finally AVF. Okay, so the precordial leads are not necessary for this calculation. Okay, so you can effectively get rid of them, which leaves us with this. Okay, now the first step to calculating an axis is to look for the most isoelectric lead. Now, what we mean when we say that is the lead whose deflections from the isoelectric baseline, i.e. the point of 0 voltage, is the most equal. So if we look here at these complexes, you can see the standard limb leads 1, 2 and 3 are all much more positive, or at least more positive than they are negative. Now, AVF in the augmented limb leads are exactly the same, and AVR is simply that but reversed, so it's much more negative than it is positive. But if we look at the complexes in AVL, you'll see their deviations from the isoelectric baseline are relatively similar. Okay, so we can say with a relatively large degree of confidence that AVL is our most isoelectric lead. Okay, so what you want to do with that, you go to your hexaxial reference system diagram and find the lead that crosses it at 90 degrees. At 90 degrees. Okay, so if we do just that, we're all in agreement that AVL is our most isoelectric lead, and if we look down here, we'll see at 90 degrees we have lead 2. Okay, so we now go back to our ECG, look at lead 2, which is here, we'll pop that down there, and the final step is to decide whether lead 2, or the lead that crosses at 90 degrees, whatever it may be, is it positive or negative. So in this case, it should be fairly obvious that this is positive, as its deflection is upwards. Okay, so now once again we go back to our hexaxial reference system. So lead 2, if it's positive, you follow the lead towards the label that you've written, okay, towards this positive end, plus 60. Okay, if it was negative, you'd follow it this direction, okay, but because it's positive, we will go down here, and as you can see, we have landed in the normal cardiac axis region. So positive, in this case we arrive at plus 60 degrees, which is normal at 60 with a 30-degree level of accuracy. Okay, so that's how you calculate cardiac axis to 30 degrees.